We have two scientists on hand today. Wouldn't they be useful to have in your handbag? Anyway, they're here in the studio, and it's biologist Dominic Geraghty. Good afternoon, Dom.
How you doing?
Not too bad. And we've also got physicist Denis Visentin. Hello, Denis.
G'day.
So do you two get on? Biologists?
No.
Hate each other.
No, hate is good.
Okay, well, we're going to start. If you've got a question at home, 1300 222 936, or you can text it to 0438 922 936. Now, this is a question that I canvassed with Leon Compton, our mornings presenter this morning, and he rubbished me, I think was pretty much what he did. Why is it always 11 minutes past when I look at the clock?
Well, I'm glad we're dealing with the big issues here.
That we are.
Dom, do you want to have a first go with this one?
Oh, I always think of the Matrix when I think of questions like that. In other words, would you have knocked over the jar on the table if you hadn't actually thought about it? So we train our brains to do things. So if you have a regularly look at the clock and look at the clock on a daily basis, you will actually train your brain to do that, and obviously it'll appear as if it's happening by some weird sort of twist of fate.
So I actually am looking at the clock at 11 past because I've trained myself.
There's a guy called Norman Doidge who talks about how we can retrain our brain to do different things. For example, if you have a stroke, and we can actually make the opposite side of our brain work in a different way, and we have to train it. So that's what we do with people who've had brain injury or anything like that. So it's the same concept. You're training your brain, and you will just constantly do it, but unconsciously look at the clock at the same time.
Any idea why it's 11 past for me and not 20 past?
No idea. I wake up every morning at 3:30 in the morning because the plane flies over.
Always gets back to blaming airlines, doesn't it?
Exactly.
Well, this might also answer my next question. For people who have that thing where they always wake up 1 minute or 2 minutes before their alarm goes off.
Well, one possible explanation. Actually, I've got a friend who said that her dog was a genius. She was very, very excited. Susan, if you're listening. Her dog wakes up at 6 o'clock every morning, and it still woke up at 6 o'clock exactly. When it changed over to daylight saving, she thought the dog was an absolute genius and can tell the time, of course. But she lives across the road from a post office, so I suggested it's probably the postie that's actually waking the dog up. So one suggestion would be that, you know, if you're training yourself to wake up at a particular time, then you're going to be particularly heightened for the stimuli that are happening around that time. So if there are things, noises or events that are happening around you, then you'll have a heightened response to those sorts of things.
What happens, though, when on the weekend you don't wake up?
You've also got a response to not wake up on the weekend.
Well, yeah, you train your brain. We call them our circadian rhythms or our biorhythms, and the whole body operates, and our whole lives operate around these particular rhythms.
We've got Ray, who's called through from Launceston with a complicated science question, so I hope you guys are prepared. Hi, Ray. How are you? Hello, Ray? Are you there, Ray?
G'day.
How are you going? What's your question?
Well, it's a long, drawn-out one, actually.
Go for it.
It's the Earth goes round on its axis, right?
Mm-hmm.
And anything that goes on an axis, if you change the setup of it, it would make a difference to the way it goes round. If that makes sense. I'm not very technical, but
we're getting nods here. They know what I mean.
Looking at the billions and billions and billions of tons of iron ore and copper and whatever else comes out of the southern hemisphere, of the southern part of our world, and goes to the northern part of the world, wouldn't you think that that amount of change of weight would have some impact on the world's ability to maintain its axis?
I've got what you're talking about, Ray. So because we're changing the weight ratios of where things are in the world, and I guess, you know, you could talk about it in any way, more houses being built, more people being born, why isn't it skewing the way that we spin around on the axis?
Because despite the fact that it seems like we're taking an enormous amount out, it's minuscule compared to the actual weight of the Earth. So it's a very, very small fraction of the mass. And though going to the northern hemisphere, it's probably being made into goods or burnt or something that is redistributing it anyway. But yeah, the tiny amount that's being taken out would have a minuscule effect.
As opposed to the 3 kilos that I've put on over the last few months, which has completely changed my centre of gravity.
Is there a tipping point?
Yeah, but it would be a long way off.
Okay, we've got a bit to go. Another one that's come through on the text on 0438 922 936. Is light made up of particles or waves?
Both.
Okay, a bit more explanation?
Well, modern quantum mechanics demonstrates that our description of things as either being particles or all waves or bits of energy is misleading, and actually anything can be both a particle and a wave, or has both particle and wave properties depending on how you look at it. So a wave, it has electromagnetic, light is an electromagnetic wave, and you can observe those properties. It has interference effects, for instance, but it also has particle properties, and so you can look at individual photons. So yeah, it's a bit weird and odd and outside our normal range of experience, because the things that are sort of on our level don't show these sort of strange quantum effects. But once you get down there, it starts getting once you get to the very, very small, it starts getting very odd.
I hope that's answered the question, and I think we've got probably, the big question here from Jake from Campania. What existed before the Big Bang?
I pause.
As I'm sure many a scientist has paused before.
One answer to this is that if we talk about things existing, that is a description about our universe. And so our universe is closed. And so what happened before the Big Bang, both space and time were created at the Big Bang. So nothing existed before because there was no space or time for it to exist in. Is a short answer, but it's
no
an interesting...
trees on hills to sit underneath to consider something like that.
Correct.
Okay. Oh, we're getting there. It's 2:12. My guests are a couple of scientists. We've got biologist Dom Geraghty and also physicist Denis Visentin. Perhaps this is one to you, Dom. I'm not quite sure. Phil from Margate's called through and says that you never hear of someone getting a tumour on their heart, and yet you get it everywhere else. What's the reason that you don't seem to get cancer of the heart?
Oh, the simple answer is you do.
Okay.
People get cancers of the heart.
Are there any reasons why tumours, are tumours more common in certain parts of the body than other parts?
Cells that have a rapid turnover rate are more inclined to people develop bowel cancer, lung cancer, and so on. So where you've got areas, the lung doesn't turn over that quickly, but for example, the gut does, skin does. So all of those tissues where we have rapid replication are more prone to getting out of sync, and that's a very, very simple and not totally accurate explanation, whereas heart cells don't.
1300 222 936 if you've got a question for Dom or Denis. 1300 222 936. Another one's come through from Laura in Trevelyan. How come there's a double rainbow sometimes?
Well, a rainbow is created when the light that is behind you is bouncing off water droplets, and it actually bounces twice off the back of the water droplet. So when you're looking at a normal rainbow, the water droplet is reflecting the light and splitting the light into its different colours. Now, if you look above the rainbow, what you'll sometimes see is a double rainbow. And the second rainbow involves a triple reflection, where the water is bouncing off the back of the light is bouncing off the back of the water droplet 3 times. Now, the interesting thing is, if you look at that second rainbow, it's actually up the other way. So the colours are inverted because of that extra reflection.
That.
Have a good look.
Very clever.
Right, he's very clever.
You don't have to wait for it to rain, of course. You can just get out with a hose, make sure the water's behind you, and create your own rainbow.
So the rainbow on top has the red in the inside?
Yes.
There you go. I'm hoping that it's rain and sunshine. Why does it sometimes reflect 3 times?
Well, it'll always reflect 3 times. It's just depending on the height and where your eyes are. So you'll see the triple reflection being higher because that's where the light is coming in and hitting your eyes. You'll see the double reflection lower in the sky because you're standing at exactly the right point to see it.
If you've got a question, these are the men to answer it. We've got Dom and Denis in here. Does this make you nervous when you're taking questions like this?
I'm sweating profusely.
No. I'm an Irishman. I like talking.
1300 222 936. 1300 222 936. Sean is in Hobart. Good afternoon, Sean.
Good afternoon. How are we?
All right. What's your question?
My question is, if there's a jumbo jet flying in the sky at 20,000 feet and the emergency door gets blown off, do the people inside the plane, all particles in the plane, get sucked out or blown out?
Ooh, sucked out. Thank you, Sean. Sucked out or blown out?
A bit of both, probably. The air is trying to be sucked out, but my guess is that it'll probably also have a tendency to get pushed back in, and so whether it's imploding or exploding is probably a moot point at that point.
You're looking at the biologist for this, Dom?
I'm thinking sucked out, but that's just my view. Pressure, the difference in pressures. Because if a door blows off, basically you've got a pressurised chamber flying at very, very high altitude where the actual external pressure is very, very low, and as a result, as the door gets blown off, my view would be that you'd be sucked out of the plane rather than blown out. But we won't argue.
You like to pick holes in his argument.
Yes, I can't let him have that one. Whether the low pressure outside is sucking you out or the high pressure inside is pushing you out is a matter of semantics.
Yeah, but you're
perhaps.
also talking about volume. So the volume of the atmosphere is a lot greater than the volume of the inside of the plane. So I think that would be the dominant force.
Yeah, I'll let that one slide.
Okay. We've got a question from Van. If we have a disc and we run a diameter across that disc, each time a disc turns, the outside is going at a higher speed than the inside until you get to the centre, where, as you continue back to the outside of the disc, the speed then increases. This is the question, though. Is there a point at the very centre where something isn't moving?
Well, I guess it depends on what you mean by isn't moving. The entire disc is rotating, so we'd say it has angular speed and has a constant angular speed. But of course, the linear speed, the speed in a straight line, is different depending on where you are. So certainly if you're, say, on a merry-go-round and you're at the edge, you're moving much faster. But if you're in the middle, you're still turning around. So, you're still moving even though you're on the same spot. So yes and no is the answer to that.
Typical physicist.
Depends whether you're talking about angular motion or linear motion.
Chris has called through from Pipers Brook at 2:17. Good afternoon, Chris.
Good afternoon.
What's your question?
Well, it's to do with radio waves, and I've always understood radio waves by the way, like if you throw a stone into the pond, they ripple through and you're picking up the differential in the peaks and troughs and is receiving it, except you've got an extra dimension because you're doing it in 6 axes rather than 2. What is the medium that the radio waves is actually vibrating through? Because you've got the air and all that around the planet. When you get out into space, there's allegedly nothing. What is the medium that the radio waves are vibrating through?
Okay, thank you, Chris. I think we're going to refer to Denis on this one.
Well, you don't need a medium apart from space for radio waves. Radio waves are just a particular form of light, very low frequency light, and so the light can travel through space, and radio waves can do that as well. So the radio waves will travel a little bit slower through air than they would through space, but they travel by their electromagnetic properties. And so you don't need any particular medium for the radio waves to travel apart from space itself.
Chris, has that answered things?
Not really, but...
At least you're honest. That's what we like, honesty this afternoon. Jimmy's called through with a question. Why does it use more energy to create heat rather than to create light or turn fans on? Whoa, that's a pause for effect, because this answer is going to be phenomenal. Or does it take more energy to create heat?
Well, when you've got a light globe, a lot of the energy is actually going into generating heat rather than generating light. I guess the light required for a particular task, say to do your, to be able to read, requires a lot less energy, say, than to heat up the room. So it's not that the energy, it's still the same amount of energy. We've got this law of conservation of energy. You can't create it or destroy it. Except in special circumstances.
I know that.
But yeah, it's just in order to perform those heating tasks, firstly you'd lose a lot of heat from that heating task, so the heat will tend to dissipate. So if you're heating up some water, for instance, some of that is just being lost to the air around you, so you've got to keep pumping more heat in. But probably a lot of the things that we use energy for, like lighting, just don't require as much energy.
There's the answer. It's 2:20. I'm Penny Terry, and during your afternoon today, we're celebrating the start of Science Week and getting your questions answered. One that came through earlier today is, why does it feel hard to move your hands when it's cold? When your hands are cold?
Oh, when your hands are cold, basically it slows down your metabolic processes. So basically the machinery that's generating energy is not actually ticking over, if you like. Your batteries are not firing at full speed, and as a result, your muscles don't contract as easily. If you cool any part of the body, it'll operate at much lower, much lower frequency, much lower speed. Everything just slows down. Cold.
On a cold day, does your brain work slower?
Your brain is insulated. I mean, when your brain is one of the most highly protected organs in the human body. We've got a skull, and we've got these layers of protective coatings around it, which have fluid inside them. So your brain is very, very well insulated. So, no, highly unlikely.
It'd have to be pretty cold.
I think you'd have to be very, very cold.
Okay. We've got John in Hobart. He's got a theory that he'd like to test on you guys. Good afternoon, John.
Good afternoon. I suppose it's not really a theory, it's just a concept. If we were to look at an atom closely enough, beyond anything we've got on the world available at the moment, what would be the chances of actually finding life living on that atom? Maybe even planets, maybe even people, maybe the same complexity of life that we've got on our atoms, and then you look at their atoms and there's another chain of life there. And then working the other way, could we be living our life on someone's atom, maybe on someone's fingernail, and the chain goes both ways.
It's Guy in theory, isn't it?
Has it got a name?
Perhaps. Actually, a Nobel Prize-winning physicist, Richard Feynman, gave a lecture called "There's a Lot of Room at the Bottom," and he was talking about what sorts of things can we have at the levels of atoms, and it's an odd place to live. We've got some atom imaging technologies now, so we can actually look at atoms and we can observe them directly, which we haven't been able to do up until the last 10, 15 years. I don't think there can be life down there because life requires working parts, and the concept of working parts below the level of an atom is very, very unlikely. So I think down at that level, you're actually getting to the point where you couldn't actually, have things that had interesting working parts. So I think I find it unlikely that there will be life at that level. But certainly we can have life at sort of levels slightly higher than the atom. And so, viruses, for instance. How big is a virus?
Small.
Sure. Small. They're little.
They're little. But could be living in a virus, I guess, to go on from...
Yeah, I think that's a much more reasonable expectation, that our entire universe could just be a little blob on some flea.
There are complexities that people talk about, that we're just an organism, and for example, war in one part of the planet is almost like a cancer, so that we're part of another super organism, which is the same. So going up rather than down towards atomic size, we're going up towards bigger and bigger sizes, which is, I think it's a bit of Guy. Is it Guy in theory?
Guy in theory is about the Earth is one organism.
Yeah, same concept, yeah.
Okay. Cheryl in Launceston, how do you make something out of nothing? I wonder if she's talking about the Big Bang Theory or if she's having a bit of fun.
It has been proposed that you can make a universe out of nothing, and actually there's some idea that our universe may have been made out of nothing, and perhaps the entire energy of our universe adds up to zero, which seems quite an odd concept, but it's something that's...
So whether that universe is a part of a virus or not.
That's right.
Yeah, okay.
So it seems a possibility that we can create universes out of nothing. We can certainly create particles out of the vacuum. So we have particle and antiparticle pairs being created all the time, essentially out of nothing, out of the vacuum of space. So the idea that things will pop into existence and then pop back out of existence, probably like our good selves, is not an alien concept to the physicists. So the idea that the entire universe might be this sort of borrowing of some energy to create something interesting for a very short period of time, a few billion years or so, is a possibility and an interesting area of research in cosmology.
Now, I'm very aware that you're getting a lot of questions here, Denis, and Dom's here
Physicists are a lot more interesting.
I know more stuff.
Yeah, smarter.
If you've got a question directed towards by 936, but carrying on from this something of nothing, out of nothing, Alan's been on the text on 0438 922 936, and he says, "Hi Penny, there's something wrong with the Big Bang Theory. Energy can neither be created nor destroyed, and for every action there's an equal and opposite reaction." He says he's not religious, he's just thinking.
Yeah, well, they're good thoughts. The idea that nothing can be created out of nothing, that we can't create things out of nothing, seems quite reasonable, but it might not necessarily be the entire story. We certainly know that we can create things for short periods of time out of the vacuum. So it's possible that we could create a whole universe out of that. And What was the second part of the question? I didn't...
For every action, there's an equal and opposite reaction.
Well, I guess this is talking about the idea that everything has a cause, perhaps. And if we look back, we look at causes of the events that occurred, and if we've got this whole universe, we want to know what the cause of that universe is. So there had to be something, this idea there had to be something before that caused it. But of course, that doesn't solve our problem. We have to find a cause for that cause. There's an infinite regression there.
And it's a current theory as well. Don't forget that one thing about science is that things change. I mean, the classic biological question that used to be asked, how much of your brain do you use? And people used to always say, 1%. Where did you hear that? Can't remember. No idea. Because it has changed. We now know that we use a lot more of our brain.
How much do we use?
A lot more.
Okay.
Because I would never give a constant number for it, because we know that it's changing all the time, and people's abilities to assimilate information, the high speed at which my daughter, for example, plays with information on various different platforms, it's amazing. So it's the ability to change, and that's what makes science interesting, always makes science interesting.
We talked about it not that long ago, actually. I think it was Dr. Karl who said that, well, I'm sure he wasn't the first person that said it, but he mentioned it here on the radio a few weeks ago, that every generation is getting a higher IQ. Is that a result of us being able to use more of our brain, or just use it differently?
I think it's evolution as well, but also we are being exposed to a lot more information. Nutrition. I mean, if you look at, I go in and I teach a class, the number of people that are over 6'2", 6'3", I'm using imperial measures there, by the way, to show how old I am, and I walk in, they're getting taller, they're getting stronger, they're getting faster, and even without drugs in sport, for example, we are becoming faster as a human race. We keep constantly breaking records. So it's actually evolution, and I think the human brain, is also evolving.
I remember that one of the beautiful features of science is that we stand on the shoulders of giants. And so, Isaac Newton discovered more in physics than perhaps anyone else, but a first-year undergraduate in physics knows more than Isaac Newton ever did. So, and this is continually growing, and something that would have taken many, many years of study to learn, now we can do in a short period of time. Unfortunately, there's just so much to teach people.
Too much.
That's what Science Week is about, and we're hopefully helping out. A biological question, perhaps. I've got no idea where this one fits in. Why do cats always fall on their feet, and how come they can only do it 9 times?
This is actually fantastic, because we've got the newest adopted member of my household happens to be a cat, Tempe.
Oh no, you've been testing. You've been hypothesising.
Well, no, actually she demonstrated for me last night. She took a leap onto the windowsill and missed, and did actually land on her feet. It's because a cat has got an incredibly flexible vertebral column, as opposed to humans, which are very restricted by our muscles and by the way in which we have our vertebral column is set up. And secondly, a cat doesn't have a clavicle, so it doesn't actually have a collarbone. So it's actually able to rotate in space very, very quickly. Humans can do it, but they need the critical distance that they need to right themselves from falling from a height is a lot greater. A cat can do it. I think the minimum is around about 30 centimetres, 12 inches in the old terms.
Do not try this at home, because we take no responsibility for broken cats.
I was about to say, don't try and break your cat, because not all cats are as flexible as Tempe.
Also, don't do it with a kitten. They learn. It's called the righting reflex, and they learn it at a certain age. I don't know what the age is, but the kittens can't do it.
About 12 weeks.
Kittens can't do it. No collarbones. They'd be very good at playing, I don't know.
They've got a collarbone, but it's not the same. Yeah, it would be good.
Because they're always doing shoulder injuries and stuff. How does wine turn into sparkling wine?
You're the wine expert.
You're
just the drinker.
Nothing to do with your job.
Excuse me, I'm an Irishman. You're an Italian. You know why? It's just carbonation. It's just carbon dioxide. The actual process of fermentation generates. They allow the gas to stay in there, and that's me being very, very. I only like drinking wine. I don't actually make it. So carbonation.
But of course, you can put the carbon dioxide in it later if you want to do it the cheap way.
Cheap way, yeah.
Kenny's asked, if I'm shrunk to the size of an atom, am I ever to see any light?
Probably not see, because the photons that are hitting you would be significantly large compared to your size. So you're probably going to be buffeted by light rather than
be fried. Actually,
yeah. Yes. Once you absorb the first photon, that's probably the end of you.
The other question that I mentioned before, people talk about their arthritis hurting more depending on the weather, or they can feel it more. What's that about? Is it true? Is it happening?
I mean, people often talk about my cold weather knee or something like that. it's a too complicated an answer in many respects, but joints, everything slows down in the cold, so you probably feel less capable of generating heat when you're cold, and heat is one of the greatest treatments you can have for any form of inflammatory disease. If you put your neck out, talk for your collarbone, you will actually put a hot compress on it.
Something that a cat will never need.
Something that a cat will never need. So effectively you're saying is that heat is a very therapeutic agent when it comes to any form of inflammatory disease, and so if you're feeling cold, you will probably find that you're feeling that pain a little bit more.
And my final question today, because we do need to keep going, but why does it appear that the wheels are going backwards on cars when you see them on television?
Okay, well, when you're looking at something, it is a little bit complicated without being able to draw it. When you're looking at something in real life, you're getting the information all the time. When you're looking at it on television, you're getting it at a certain frame rate. So you're just seeing little still shots, very many still shots in a given time, but you're seeing little flashes of what's going on. So you're not seeing the wheel all the time, you're seeing certain moments of that wheel. Now imagine that the wheel is doing one exact rotation for each of those frames. Then you'll see that wheel completely stationary because the wheel is doing one complete rotation, it looks exactly the same as it did in the last frame, and so on and so on and so on. Now, if the wheel is turning a little bit faster than that frame rate, then what you'll see is the wheel slowly turning forward because it'll always be slightly advanced. If it's turning slightly slower than the frame rate, then it'll be slightly behind at each time, and so it will appear to be slowly moving backwards. So actually it's not all that wheels always look like they're going backwards, that they'll sometimes go from looking stationary, looking like they're going forwards quite slowly, and then looking like they're going backwards slowly. So you get this quite odd effect that's associated with a frame rate.
And high-speed digital television, it probably wouldn't really happen because the old television, analog, was 26 frames per second, wasn't it? Or something like that?
Yeah.
So it'll probably be different with digital TV. Yeah.
Well, I was going to say, that's why I put sometimes in there, because it seems to have vanished. They're going
digital
forward.
Television.
Yeah.
The sampling rate is much, much higher, and therefore you're actually getting real-time imaging.
And from Angela, she can have the final question today. As a physicist and biologist, are you ever able to suspend disbelief long enough to enjoy Star Trek?
Yeah.
I think I was the only person as a physics undergrad that didn't like Star Trek. I had it quite naff.
Star Trek's naff from a physicist. First time you'll hear that. Thank you very much for coming in and helping us to launch Science Week. Just before we go, Dom, you're very involved with a debate tonight. Tell us about that.
At the Annex Theatre, but it's booked out, it's sold out, it's art but not science will save the world.
Oh, so you're arguing for art, of course.
Of course, yeah, definitely, yeah.